Hi, thanks for joining me. Today I'm going to be going over problem 2 from week 4 of the Invariants Summer Puzzle Competition. As always, I'll leave a link in the description below to the Facebook page of the Invariants where you can find more details about the competition. Anyway, this is the problem we have today. We want to find all pairs of positive integers n and m, with n being at least 2, such that n factorial does not divide this guy here. So this is the product from I equals 1 to n minus 1 of m to the I plus I factorial in brackets, all raised to the floor of n divided by I. So kind of a mouthful here, but it's just kind of a product of terms from I equals 1 to n minus 1 of m to the I plus I factorial raised to the floor of n over I. So if you've not seen this floor function before, all it means is you're taking the greatest integer less than or equal to the input. So for example, the floor of pi, because pi is 3.14, the floor of pi will be 3 because 3 is the biggest integer smaller than pi, or smaller than or equal to pi. So the floor of pi is 3, and the floor of any integer is just the integer itself, so the floor of 3 is just 3. So that's just if you've not seen the floor function before. Anyway, if you want to have a go at this problem, pause the video now and give it a go for yourself, and I'm going to jump straight into a solution. Okay, so the first thing I want to do is introduce this function fnm, and it's defined to be equal to the product from I equals 1 to n minus 1 of m to the I plus I factorial raised to the floor of n over I. Now, what I'm next going to do is introduce valuation functions. So if you've not seen them before, generally they look a bit like this, so v sub p, and p here is a prime number, and this is a function. It takes in a positive integer and spits out a non-negative integer, and how it works is it tells you the largest power of p that divides your input. So in other words, the number of times you can divide your input by p. So for example, if we've got v3 of 18, we want to know the largest power of 3 that divides 18. Well, 3 squared is 9 and that divides 18, but 3 cubed is 27 and that doesn't divide 18. So that means the largest power of 3 that divides 18 is 3 squared. So 3 to the power of 2. So that means that v3 18 is 2. So that's kind of how we define VP. The next thing I want to do is find an upper bound of VP n factorial. So VP of n factorial. Now this guy here, we can actually write out explicitly as in terms of an infinite series. This is the sum from I equals 1 to infinity of n divided by p to the I, but then we take the floor of that guy there. Now, if you've not seen this before, hopefully I can give you a brief explanation as to why this works, but if you want to see it in a bit more detail, I've explained it in a previous video of mine where I try and compute the number of zeros at the end of the number 2020 factorial. So I'll leave a link for that in the description below, and if you watch that, hopefully this will make a bit more sense. But essentially, we want to know the number of times we can divide our number n factorial by p. So if you just write out n factorial, it's 1 times 2 times 3 times 4 times so on, all the way up to n minus 1, n minus 2, n minus 1 times n. So we firstly ask how many multiples of p are there in this kind of product here. Well, there's going to be exactly n over p, but the floor of that. Okay, because of course you're going to get one every p times, and how many sort of times can you fit p in here? It's n over p and then the floor of that. But then you've got to consider, what if there's a p squared in here? Then that's going to constitute 2 towards my kind of number of times I can divide by p. But I've only counted 1 so far, so I've got to add 1 for every sort of square, every p squared there is in here. So I have to add on an n over p squared floor of that. In other words, that's the number of times a multiple of p squared occurs in this product here. And the exact same thing for p cubed. And so on. And that's how we get this thing here. That I is supposed to be in the exponent, sorry. Like this. So that's where this formula here comes from. So if you want to see that in a bit more detail, check out my 2020 factorial video, link in the description. But let's continue with this guy here. So we want to find an upper bound to VP n factorial. Well, one thing we can do straight away is say that this thing here is less than or equal to the sum from I equals 1 to infinity of n divided by p to the I. Okay, that's just essentially getting rid of the floors because we know this guy here is less than or equal to that guy here. Okay, well this thing here we can go a little bit better and essentially factor out the n, and then we know that that's just a geometric series, and you can go ahead and work that out. That is just n divided by 1 minus p, like so. So this guy here, VP n factorial is less than or equal to this guy here, and this guy here just equals n divided by 1 minus p, just using your geometric series formula. So we know that VP n factorial is less than or equal to this guy here. But notice that VP n factorial must be a non-negative integer, but in particular an integer. But this guy here may not be an integer. So we can make our bound even better by just taking the floor of this guy here. So this guy here might be a little bit more than an integer, so like 3.2 or something. But because we know VP n factorial is going to be an integer, we know that it's going to be less than or equal to and we know it's less than this guy here, so it must be less than or equal to the biggest integer, smaller than this guy here, namely the floor of n over 1 minus p. Anyway, that's a quick upper bound on VP n factorial proved. Let me clean up the whiteboard and we'll continue. Okay, so up here I've written down what we defined fnm to be, and I've also written down what we just proved. A VP of n factorial is at most the floor of n over p minus 1. The next thing we're going to do is consider a prime p with p being less than or equal to n and p not dividing m. So in other words, m is not a multiple of p. Then, by Fermat's little theorem, we know that m to the p minus 1 is going to be congruent to 1 mod p. And similarly, by Wilson's theorem, p minus 1 factorial is going to be congruent to minus 1 mod p. So this is by Fermat's little theorem, and this is by Wilson's theorem. If you've not seen either of those before, go and look them up. They're very fundamental theorems in number theory. Anyway, continuing, what we're going to do is add these two lines up. And on the left-hand side, we get m to the p minus 1 plus p minus 1 factorial. And that's going to be congruent to 1 minus 1, which of course is 0, mod p. So what that tells us is that m to the p minus 1 plus p minus 1 factorial is going to be a multiple of p. So I can write it as lambda times p, where lambda is just some positive integer. But now what we notice is that if we go back to our fnm here, because p is less than or equal to n, then certainly p minus 1 is going to be less than or equal to n minus 1. So p minus 1 is going to be in this kind of index here, so it's going to be some I. But now notice that when I equals p minus 1, we've got m to the p minus 1 plus p minus 1 factorial, which we know is a multiple of p now. It's lambda times p, and then we're raising it to the n over n over p minus 1 floor power. So what that tells us is that fnm is going to be some number mu, so some positive integer mu, and this mu here just corresponds to the other terms in the product, so that when I doesn't equal p minus 1, and then the case where I equals p minus 1, we get lambda p raised to the n over p minus 1, and then floor of that, like so. So this is what fnm equals, but notice now that in n factorial, because p is less than or equal to n, p will appear in the product of n factorial, but we know that it's going to appear vp n factorial times. So that's the number of times we can essentially factor out a p from vp n factorial. But notice that from this guy here, fnm, we can take out more lots of vp n factorial. We can take out more lots of p from fnm, because vp of fnm then, just by looking at this thing here, mu might be a multiple of p, we don't know, but from here we can clearly see we've got at least n over p minus 1 floor coming from this guy here, p to the n over p minus 1 floor, and we know from what we just previously showed that this thing here is bigger than or equal to vp of n factorial. So that means we've got more, so kind of the power of our prime p in fnm is going to be at least that of that in n factorial. So then that means that n factorial, at least this particular prime p part of it, must divide fnm. So if p is a prime with p being less than or equal to m and p not dividing m, then we know that the number of times the prime divides n factorial will certainly be at least that of the number of primes that come in fnm. I hope that's made sense. Next thing I'm going to do is clean up the whiteboard and prove a very similar thing, or state a very similar thing about when p does divide m, and hopefully you can bring these two ideas together and make a bit more sense of all this. Let me clean up the whiteboard and we'll continue. Okay, so I've written down here what we just proved. If p is a prime with p being at most n and p not dividing m, then vp of fnm is bigger than or equal to vp of n factorial. Now I've written down a very similar looking claim here. If p is a prime, but now p is strictly less than n, and p divides m, then VP of FNM is bigger than or equal to VP of n factorial. Now I've written ... here because I'm not going to prove it. The proof to this is quite similar to this. It's a little bit more technical, but I'm sure you can all cope. I'll leave it as an exercise to you guys to prove this claim here, and I'm just going to continue as if it were proven. But now notice that we've almost essentially solved the problem, because I now claim that NM, the thing we're trying to work out all pairs for, this must be of the form PCP, where P is a prime and C a positive integer. Why is this true? Well, let's see why we must have n being prime. Well, if n wasn't prime, then we know what we can do is write n factorial as a product of prime. So n factorial, when we write it out, is going to be p1 to some alpha 1 times p2 to some alpha 2 times so on all the way up to pk to some alpha k, like so. But notice that all of these pi's, because n is not prime, or what we're assuming, if n is not prime, so if n not prime, so then all of these pi's will be strictly less than n. Then we can apply either this lemma or this one, depending on whether p divides each of the pi, whether the particular pi divides m or it doesn't. But either way, we get the same conclusion, that VP of FNM is bigger than or equal to VP of n factorial. So what that means is that for each of these primes pi, we know that FNM is going to have a p1 in it to some power, which I'm going to call beta 1. But we know beta 1 here is going to be, because of this inequality here, is going to be bigger than or equal to alpha 1. Same holds for p2, to the beta 2. Beta 2 will be bigger than or equal to alpha 2. And so on, all the way up to pk to the beta k. And beta k will be bigger than or equal to alpha k because of this inequality here. But then just stare at this 1 second, you'll be able to see that n factorial divides FNM then. And we don't want those. We want the case where n factorial does divide FNM. So we must have that n is prime, by essentially combining these two things together. And for a similar reason, we must have that m is a multiple of n, because if m is not a multiple of n, then we can just apply this lemma here. We can just apply this lemma here and we'll get a very similar result. So for a pair nm to be like a valid pair, that we must have that nm is of the form pcp, like so. So p is a prime and cp is essentially a multiple of that prime. But of course that doesn't solve our problem, because we need to check that these guys work. So in other words, if we let n be a prime p and m be just a multiple of a prime p, then fnm is not divisible by n factorial. We still need to check that. Let's check that, but let me clear up the whiteboard and then we'll continue. Okay, so we've just showed that if n factorial does not divide fnm, then we must have that nm is of the form pcp. The last thing we have to do is show the converse. So if nm takes the form pcp, so n is a prime and m is a multiple of that prime, then n factorial does not divide fnm. And thankfully that's a lot easier to prove. So suppose nm is of this form, so pcp, then what we're going to do is just consider fnm mod n factorial, so mod p factorial. So well, fnm, notice, is, actually we're going to consider it mod p first, and notice that because we're doing the product from I equals 1 to now p minus 1 of m to the I, which is cp to the I plus I factorial, and then we're raising it to some power, n over I, and then the floor of that, we're going to consider this mod p. But notice obviously when we consider it mod p, this term here vanishes, so cp to the I vanishes, so we get a congruency. So we're just considering I factorial raised to some positive integer power. But notice that because we're looking at the product from I equals 1 to p minus 1 and p is a prime, that means none of these guys here are going to be a multiple of, or none of these guys here are going to be divisible by p, because they're strictly less than p and p is a prime. So when we look at their factorials, we're going to get a similar thing. None of these factorials are going to be divisible by p. So all in all, this guy here is not going to be congruent to 0 mod p. So that means that fnm is not congruent to 0 mod p. So that means that fnm is not divisible by p. So certainly it's not divisible by p factorial. So we get this guy here, because if it's not divisible by p, there's no way it's going to be divisible by p factorial. Anyway, I hope this has all made sense, and that solves our problem, by the way. So nm must be of the form prime, comma, multiple of that prime, and yeah, and it's an if and only if. Right, I'm waffling now. I hope that's all made sense. Thank you for watching. I'll catch you in the next one. Have a great day.